So Sergey received a PhD from Stanford University 2014, and then he joined UC Berkeley as a faculty in fall 2016. His work focuses on machine learning for decision-making and control, with an emphasis on deep learning and reinforcement learning algorithms. Applications of his work include autonomous robots and vehicles, as well as computer vision and graphics. His research includes developing algorithms for end-to-end training of deep neural network policies that combine perception and control, scalable algorithms for inverse reinforcement learning, deep reinforcement learning, and more. His work has been featured in many popular press outlets, including the New York Times, BBC, MIT Technology Review, and Bloomberg Business. And I will also add that he's an extremely prolific author, and he has done amazing work on reinforcement learning as probabilistic inference, and more recently in offline RL. So I will pass the floor to him. I see he already shared screen. Sergey, thanks again for accepting our invitation.
Great, thank you for the introduction. All right, and everyone can hear me all right? Yes, okay.
Yes, we can hear you.
So today I'm going to talk about some of the intersections between planning and reinforcement learning. And to start off with, well, let's talk a little bit about what is kind of the first thing we think of when we think about reinforcement learning, or in some cases, when we think about planning. So, I think that a very common perception of what reinforcement learning means is something like this, right? So you have some perhaps physically nuanced behavior that you'd like your agent to learn, but it's not a particularly cognitively demanding behavior. So it's something that is, fairly agile, fairly quick, but doesn't require a lot of reasoning about future consequences of your actions. And it's learned through reinforcement, through reward. Whereas planning, we think of intuitively as something that requires a little bit more foresight, a little bit more kind of, cognitive processing. So, the classic example is from the Wolfgang Kohler study. Is the monkey that was placed in a room where there's a banana hanging from the ceiling, and the monkey spends some time pondering its situation, then fetches some boxes, stacks those boxes, and climbs up and gets the banana, right? So when we look at this, we say, oh, the monkey was doing something very intelligent, maybe more intelligent than that seal in the previous video, and the monkey was really planning. But of course, in reality, it's not that simple. It's not that there's a very clean divide between learned behaviors, and, in the case of animals, classical conditioning, and this sort of planning process. So this is an experiment by Epstein and colleagues from 1984 that was, somewhat intentionally meant to undermine the message from that monkey experiment. So here there's a pigeon that was trained through essentially classical conditioning to do a variety of behaviors, such as peck at bananas, peck at boxes, also not fly. So, the banana is a plastic banana, so pigeons don't really have any reason to want to peck at plastic bananas. They can also fly, but this pigeon was trained through reinforcement not to do that. And the experiment is meant to show that through a combination of these reinforced skills, it is actually quite possible for a pigeon, who conventionally wouldn't be thought of as capable of particularly insightful planning, to figure out how to solve this task, where the pigeon pecks at the box enough that eventually gets into a position where it can stand on it and reach the banana. Okay, so we'll come back to the pigeon in a second, but the main point I wanted to make with this is that effective intelligent behavior, especially sensor-driven behavior in the real world, requires us to both be able to perform low-level control and perception and perform something that resembles planning, at least in terms of the effect. So reinforcement learning is a really great choice if you want to be able to, for example, handle complex sensory inputs, which you need to do if you're going to act intelligently in the real world. So this is a video of a robot that is grasping objects in dense clutter using sensory input. It's also important if you're going to have fine-grained closed-loop motor skills. So these are videos of quadrupedal robots that learn a variety of more agile skills through reinforcement learning. And it's also probably not controversial to say that you need planning if you want to perform behaviors that are temporally extended, that require choosing actions now that don't necessarily lead to the outcome you want right away, but get you on the path there to reach your desired destination much later in time. So then it sort of stands to reason that if we want behaviors that are effective in the real world, that use raw sensing, that use complex actuation, that exhibit agility, but at the same time can solve long horizon tasks, then we should be thinking about the intersection of reinforcement learning and planning. But we can think of it in a variety of different ways, and that pigeon experiment sort of illustrates one extreme of this. One way that I would advocate to think about this is to think of reinforcement learning as providing kind of representations that are well suited for planning. And there are many ways we can think about doing that. Even if we go back to the monkey experiment, we could say, well, the monkey used its insight to figure out how to stack those boxes and reach those bananas. But nonetheless, the monkey came at this problem equipped with a repertoire of behaviors, almost certainly from past experience, that it was able to leverage to effectively solve this task. So you could say, well, the monkey is succeeding at planning, but another way to think about it is, well, the monkey is succeeding at leveraging behaviors it learned through experience in its, in the past. Behaviors like being able to pick up boxes, being able to stack things, and also prior knowledge, perhaps from data and experience, that bananas are delicious and worth reaching for. So maybe a good mental model that we can think of for this is that we have prior experience, basically the data that the agent has collected in the past. And the prior experience might involve performing a variety of tasks, some successfully, some less so. So maybe if you're imagining a robot, maybe it knows how to cook dinner, it knows how to repair some electronics and how to clean the floor. And that past data is going to be used to learn some kind of model. Let's call it a skill model. And we'll discuss what that skill model can actually represent. And our focus in this talk will be how to take these learned skill models and somehow interface them to a high-level planning process, a planning process that's going to somehow interact with a skill model to solve longer horizon tasks. So the skill model needs to somehow expose its capabilities to the planning procedure, and the planning procedure needs to somehow decide what to tell the skill model to actually do. So the planner, in this case, likely wouldn't be able to do the low-level agile control, and it likely would need some kind of knowledge from that skill model about, what is it that it can do in this setting. So crafting this interface is really the thing that we're going to be concerned with in this talk. And I'll discuss actually three fairly different approaches for doing this. First, I'll talk about planning over learned skills. So this will be kind of a much more classical hierarchical reinforcement learning procedure, but one that is quite effective in many settings. Then I'll talk about something a little bit more fine-grained, where we'll discuss planning inside the data distribution. So here the goal will not so much be to acquire a set of skills that a planner can utilize, but rather a set of constraints that can be imposed on the planner to get it to produce behavior that is consistent with what we should believe to be possible based on the data. And then I'll actually come back to the pigeon experiment and talk about an approach that can exhibit many of the benefits of planning without actually planning at all, at least not explicitly, at least not at test time. But let's start with the more conventional approach. So let's say that we're going to take this prior data and we'll commit to a particular choice for that learned skill model. The choice we'll make is to use it to learn a policy that selects actions given a state and a goal. So this is a goal-reaching policy. And there are a variety of ways that we could design a reward function for this policy, but they'll all basically assign a higher reward if you reach a state that is similar to the goal and a lower reward if you don't. It could be as simple as just a delta function that assigns a reward of 1 for reaching the goal, some kind of reward condition policy. And you could imagine that in practice, it's much harder to learn a goal condition policy that can reach very far away goals than it is to learn one that can reach goals that are nearby. So then it's very natural to think of planning as a process of chaining these goals, where you could say, well, let's command a goal that is somewhere close by, but that a planner determines is on the path to the eventual goal. So then we'll use this low-level policy to reach nearby goals, and then use a planner to choose a sequence of those goals such that this trail of breadcrumbs actually leads to the final goal that we want to achieve. So now, of course, this is very logical and reasonable, but then we have to think about, well, what kind of capabilities do we need this goal condition policy to expose so that a planner can actually use it effectively? So how do we choose which goal to command, and what do we need to know about the goal condition policy to do that? Well, roughly speaking, what we need to know is some sort of reachability function. The planner needs to understand if it commands a particular goal, will the low-level policy actually succeed in reaching it? Or more generally, can we provide some kind of cost to that choice and then plan to minimize those costs? Now, this is not the question that the policy is answering. The policy is answering the question, what action do I take to reach this goal? Fortunately, in the course of utilizing standard value-based reinforcement learning methods, as a byproduct, we actually already get an object that is very well suited for use in planning, and that's the value function. So the value function quantifies the expected reward that we will get when we start in a particular state. And if we're learning a goal condition policy, then the value function also depends on the goal. And if you imagine that your reward function is maybe 1 for every step that you fail to reach the goal, or maybe it's 0 for every step and then 1 at the end, then the value function already gives you an estimate of the feasibility of a particular goal. So the value function is often a byproduct of standard RL algorithms like Q-learning or actor-critic methods. And if you use a reward of, let's say, -1 for every time step before the goal, then the value function directly gives you the distance to the goal in time steps. And if you use a reward of 1 for reaching the goal and 0 everywhere else, then the value function gives you the probability of reaching the goal. And in general, for most reasonable choices of reward functions, the value function will somehow quantify how feasible the goal G is from the state S. So that's what we're going to then use. We're going to use the value function as essentially a local cost for a planner. Use the value function as a negative edge cost when planning over subgoals. And there are actually multiple ways to instantiate this. This has been explored in a number of prior works. For example, one way to use this is to employ graph search. So treat previously seen states as nodes, and then edge costs on these nodes come from your value function. And then you can use a graph search algorithm. This has been explored in several prior works. Savinov et al. Used this with a supervised learning approach. Eisenbach et al. Used this with an RL approach and value functions as described here. But we could also optimize over the subgoals directly using, let's say, a trajectory optimization procedure or something like a tree search procedure. So in this case, subgoals are states, and the values between each pair of states represent the negative costs. And then we can use any method for optimizing over those states or searching over them using tree search. So this is an example of a paper that used a continuous optimization similar to model predictive control, but there are many other choices that could be employed as well. So that's the basic idea. And what I actually want to talk to you about today is some examples of how this idea can actually be utilized in a complete robotic learning system that uses low-level perception and low-level control to solve very temporally extended tasks directly in the real world. So we're going to talk about how to learn to navigate from diverse data. And of course, the data will be used to learn these goal condition skills. And then the long horizon navigation will be accomplished by means of planning. So the kinds of tasks that we're going to want to solve will look like this. You have a robot, and that robot is supposed to navigate to some goal, and the goal is indicated with an image. Maybe this is a person taking a photograph of their front door, and the robot is supposed to deliver the mail to their front door. So the problem setting is find and navigate to a given goal landmark indicated with an image using only the robot's camera observations. So maybe this is what the robot sees now. This is a picture of the goal, and it's supposed to figure out everything that needs to happen in between. And I'm going to show a lot of these satellite views in these examples. Just keep in mind that unless indicated otherwise, the satellite views are just provided for your reference. The robot is actually doing this using first-person images. So we're going to train a model, which is going to be very much like this goal condition policy, but it's going to operate from images. So it's going to take in the current observation that the robot sees, the current image from the camera, as well as that photograph that is provided as the goal, or an intermediate subgoal. And I'll talk about the intermediate subgoals a little bit more in a second. And then the model is going to be trained to predict the number of time steps between the current observation and the goal observation, and the current action to take. And the way we can train this model is we can take a large data set of trajectories that the robot has executed. In every trajectory, pick 2 time steps at random, treat the first one as the current image, the second one as the goal image, the number of time steps between them as the distance, and the action taken at the first image as the action. And this works reasonably well to train a model that can solve this prediction problem. Of course, this model, as I mentioned before, will only really be effective for nearby goals. Roughly speaking, you can think of this as providing reasonable estimates for goals that are kind of within line of sight. So then what we're going to do in order to reach distant goals is employ that graph search procedure I mentioned before. So we're going to initially just take a collection of images that we've previously observed in a given environment. So if this requires the robot to have gained some experience in that environment before, maybe it drove through that environment a few times already, we'll use all the images that we've collected as nodes in a graph. We'll use this model to estimate edge weights between all the pairs of images. So this will be a fairly complex, very densely connected graph, but it's still a discrete graph. So we can use any graph search procedure to find a path through this graph. And then we will command the first node on that path as the next waypoint, and then use our model to predict the action. So the model is being used in two ways here, to put the edge weights on the graph, and once you select the first node to navigate to, get the action to actually navigate to that node from your current observation. And since this model is just trained on existing data, we're actually going to use a data set that was collected for an entirely different project that was actually collected 4 months prior to these experiments, just to train up this model. So the data, you can basically think of it as everything the robot has experienced before. The model is not actually very discriminating about which data you give it, as long as there's a lot of it and it's sufficient to let it generalize. So once we've trained the model in this way, then we can actually use it to solve a variety of navigational problems in environments that have previously been explored. So this does require you to actually build the graph in the environment in advance by basically driving through that environment. But once you've done this, you can command a goal with a picture of your front door, and it will deliver a pizza or patrol between waypoints. So you can give it a sequence of images, and it will patrol between those images, navigating to each one in turn. So there it goes. Okay, but what if we want to actually use an approach like this to explore a new environment that we haven't been able to build a graph in before? So what if, for example, this is what the robot sees now, and I want to give it a goal where I want to navigate to this white door, but it hasn't explored this environment before. What can it do? Well, intuitively, if we see this door on a white building and there's a white building in the background, it's kind of natural to imagine that, well, maybe the white door is on that white building in the background. It doesn't have to be. We still need to search around, but that's kind of a reasonable candidate for something to try. So we'd like to somehow get that kind of idea from the model. So intuitively, what we would want the robot to do in this situation is execute a kind of search pattern where it'll make hypotheses about where the goal might be. If it has a pretty clear idea, it should go and check it out. But if it doesn't have a clear idea where the goal might be, it should explore this environment, basically visit places that it hasn't been to before and see if it can get a better hint for where the goal is from those new places. And we can also do this using a combination of learning and planning. But we have to modify the model from before a little bit to make it better suited for exploration. Here's how we're going to do that. We're still going to have a model that takes in the current observation and a goal observation, except that now we're going to bottleneck the goal observation through a random variable that I'm going to call ZG. And the technical approach for training this, for those of you that are familiar, is based on something called a variational information bottleneck. But you don't have to really know what a variational information bottleneck is. The main idea behind what this variable is supposed to do is give us a prior distribution over goals. So it's a latent goal variable implemented with a variational information bottleneck, and it basically supports two functionalities. One is we can sample ZG from a prior distribution. Now notice that ZG depends on the start and the goal, so you can roughly think of it as an offset. It's not a literal geometric offset, it's a latent representation of an offset between two images in the sense of reachability. So if you sample ZG from a prior, what you would expect is a underlying latent representation of potentially reachable destinations from the current start observation. And of course, you can also sample it from a posterior. You can actually give it a goal image and then find the Z that corresponds to the goal image. And that'll give you basically the same functionality as the model from before. And then we predict the distance and the action from the start image and the ZG. So the intuitive way to think about ZG is to think of it as representing a change in state, but in a latent representation without us having to actually provide like GPS coordinates and stuff like that to the robot. And then you predict your distance and action based on ZG and the start observation. Now, this whole model will be trained in exactly the same way as before. The only difference is the addition of this random variable. We're actually going to use the same exact data set. One of the things we can test with this random variable is whether it's a good way to get coverage for just random exploration. We'll do something much more clever than random exploration, but we can still test it with random exploration. So here what you're seeing is a little walled off parking lot where we commanded totally random actions, basically random navigational directions. And we got coverage with a diameter of about 10 meters. If we instead use this latent goal variable and we sample from the prior, meaning command random latent goals, random positions in the vicinity of the robot that the model thinks are reachable, then we get much better coverage. Simply commanding random goals in this case actually covers the entire parking lot. It's walled off at the top there with a truck so that it can't get out, but within the reachable region, it actually goes everywhere. So that's pretty good. We're getting meaningful, random reachable locations from this model. So then what we're going to do is we're going to use it in the context of a planner that tries to expand the fringe. So what this planner is going to do is it's going to get a target image. And if from the current observation, the model thinks it can reach the target image, it'll go for it. If not, what it will do is it'll look at the current graph and find the fringe of that graph. The fringe is defined as those nodes that have been visited very rarely, and it will navigate to the fringe. And if it's already on the fringe, then we'll sample a random latent goal using that bottleneck. So this allows it to basically execute the search pattern. This is a fairly classic frontier expanding search procedure. And if it catches a glimpse of the goal, then it will navigate to it. So the first time it drove through that environment, it took 20 minutes to explore, and it built up this graph as it went. But after the graph is built, you can kind of think of it as this mental map that it builds of the environment. Then it can navigate to the goal again using the graph in just 20 seconds. So now this model now supports 3 functionalities. It gives you distances, it gives you the action to take, and it also allows you to sample a new node when you're on the frontier of the graph. All right, now let's take this idea even further. So far, when we've been exploring a new environment, if we're very far from the goal, basically the best thing we can do is grow the frontier, which can be very inefficient if the goal is very, very far away. So we can also borrow a very powerful concept from search, which is the use of a heuristic to incorporate inaccurate GPS and even incorporate overhead maps. And that will allow us to navigate to very distant goals. So the idea is that, like before, we're going to train this model that predicts distances and actions. Now the model will also predict an offset in terms of GPS. So now finally, we're actually going to use GPS. But we're not going to assume that GPS is perfectly accurate. And in fact, for a small scale ground robot like this, it'll have errors of 1 to 5 meters. So we're going to basically use GPS as a kind of search heuristic, but we're not going to trust it perfectly. And then during our planning procedure, we'll actually train a second neural network model whose job will be to produce a heuristic, just like in a star search. And the second model takes in 3 positions: the current estimated GPS position, the estimated GPS position of the goal, and the estimated predicted offset from the first model that basically tells us for a waypoint that you're considering, where is it relative to where you are now? It's going to look at these positions, and it's also going to look at an overhead map, basically a satellite image. And it's going to guess, is this candidate waypoint on the path to the final goal or not? And it's going to be actually a learned model. So it's going to be a map heuristic model, given a current state, a final goal, and a predicted waypoint, which could be sampled from the prior. Is it on the path to the final goal? We're going to train this using contrastive learning, using a method called InfoNCE. It's not so important what this method is, but roughly speaking, it just is trained so that the model gives high scores to waypoints that are on the path to the final goal. And that's just trained using the data you have. So you take now 3 time steps in every trajectory, make the first one be the current, the last one be the final goal, and the middle one be the waypoint, and then use that as training data. So the result is that it's a model that knows how to look at satellite pictures and guess whether a particular location is on the way to the final goal. Of course, it doesn't have to be in a direct line. So like in this example, it might be an intersection that actually goes away from the goal, but is necessary if you want to follow the road network. So now once we have this heuristic model, we can use it to actually navigate to a very distant goal by basically employing it like a heuristic in heuristic search. So you can think of it as a physical analog to A-star search. At every position that we're currently at, we're going to sample waypoints from that information bottleneck from the prior. We're going to add these waypoints to our graph. Then we'll take all the waypoints in our graph. We're going to score them by computing their heuristic distance to the goal, the final goal, as well as their distance from our current location. We'll add those 2 together, just like we do in A-star search. We'll create a queue, and then we'll navigate to the top of the queue. Now, there is a little difference here because this is a physical A-star search process, meaning the robot is actually physically navigating through the environment. So you don't always go to the thing that's on the shortest path to the goal. You have to consider your current location. So you actually choose the best distance from your current location to the node and then to the final goal. But that's just a small difference. Otherwise, the method is structurally very, very similar to A-star search. Okay, so here's a video of this in action. In the lower right, you can see the satellite image. The robot gets that satellite image as input now. In the top right, you can see the final goal. In the bottom left, you can see the first-person view from the robot. And you can see that it does like fairly reasonable things. Like it knows that it can cut through the forest because the forest is open ground. I can see that on the satellite image. sorry, through the field, but it doesn't actually want to go through the forest because there's, it doesn't know if the trees are passable. It actually makes a mistake here. So it actually will go into this little area and then backtrack because it realized that that path is blocked, and will go the longer way around and then eventually reach the destination. So this approach can be used to navigate to fairly distant goals. We've succeeded in navigating to an individual goal that's up to 1 kilometer away for a small scale robot. If we give it some checkpoints, it can drive on a hike that's 2.7 kilometers long. But it can also deal with changes. It can deal with issues where the map is incomplete. So here the map shows a path, that pink path that can reach the goal. But on a particular day, someone parked a large semi-truck that blocks that path. And it correctly figures out that it can't go through that now, and it can use this longer blue path and still reach the destination. So the map really is used as a heuristic. If we remove the map but still give it GPS coordinates, that's the pink path, it can still navigate to the goal, but of course it has to backtrack more often. So we're using all this additional information as heuristics, and we're borrowing an idea from planning, which is to use heuristic search. Now, of course, there are many other instantiations of this principle. The main idea is to have model-free skills expose their capabilities to the planner via a value function, and then the planner selects those skills, and the skills in turn select the actions. So here's an example of another paper that uses complex observations to learn a latent representation of state, but then instead of using a graph search, it actually performs a continuous optimization over those latent variables via an MPC-based trajectory optimization procedure. And that can get this quadrupedal robot to navigate to distant goals. Here's a more recent work that we did in the domain of robotic manipulation, where again, we have a latent variable representation of states. We are going to optimize over subgoals, and we'll actually use a tree structured kind of binary search style planner to perform more complex planning to execute multi-step manipulation skills like pushing an object out of the way, opening a drawer, putting an object inside the drawer, and so on. For something a little different, this is a more recent work done in collaboration with Google Research, where we actually combine some of these ideas where you have low-level skills exposing capabilities with a language model that actually reasons about the semantics of tasks. So here, the role of planning is actually performed by a language model, which takes a language instruction, figures out semantically which skills are useful for fulfilling that, and then uses the value functions of individual skills to determine which skills are applicable in the current situation. And then it selects the applicable skills based on their values, but ones that are semantically reasonable given the instruction. Okay, so that's kind of the more classic hierarchical approach. But I also want to tell you a little bit about a couple other ways that we could approach this problem, and this will be a little quicker. So I want to talk about how we can get away from having to actually learn particular skills and perform a more continuous process where we're going to actually just learn the data distribution. So this is going to be kind of a more fine-grained way to plan. We're going to take all of our prior experience, and first, let's think about how we can use this prior experience even without any planning. One very simple thing we could do is we can run an imitation learning procedure. Just train, with behavior cloning, train a model that copies the action that was taken in the data. That's a very reasonable way to use prior data. If your data actually illustrates ways to accomplish your task. So if your data looks like this, it goes from the start to your goal, and you run imitation learning, then you get a policy that you want. But of course, in reality, your data might contain a variety of different behaviors, not all of which are actually appropriate to the task you want to solve now. So in reality, your data might look like this. So here's some intuition. What if instead of just copying all of our data, we could somehow use planning to find a path that kind of combines bits of prior data? So something like this red line. The red line follows parts of the black lines, but it doesn't copy all of them. It just copies parts of ones that can be strung together to reach the goal. So it's almost like planning inside the distribution of the data. And it turns out that we can do this using a fairly simple combination of methods that look like imitation learning and methods that look like planning. But we can combine them so that we're basically planning inside of the data. And that's a very good idea because you get two benefits out of this. First, you ensure that, of course, your plan is actually physically possible, because if what you command the agent to do is a combination of things that it's already seen, well, if it's seen them, then they're possible. So that makes sense. And also, it allows you to incorporate various biases from the data. So if we're doing, for example, autonomous driving, and the data consists of good driving that follows the rules of the road, then if you stay inside the data, intuitively, you will also follow the rules of the road. So I'm going to talk about two approaches for doing this, one called the trajectory transformer and one called deep imitative models. These approaches make different assumptions and they use slightly different methodology, but they're based around the same key idea. that we're going to have two steps. The first step is to fit a density model to the data. And the second step is to do some sort of planning inside this distribution. Okay, so let's talk about the trajectory transformer first. This is a recent approach that's meant to be essentially a model-based offline reinforcement learning method. So the idea in the trajectory transformer is to take a trajectory from your data and tokenize it, which means that we take every dimension of every state in action, and these are low-level trajectories, so they're basically vectors of states and actions. We break them up by dimension, and then we discretize every dimension. So this produces a very long sequence, but it's a discrete sequence that can be used with very powerful, recently developed sequence models, such as transformers. And this gives us a very accurate density estimation at the trajectory level. Now, this density estimator doesn't distinguish between states and actions. It's just taking the whole thing, tokenizing the whole thing, and then modeling the distribution. But it gives you a very accurate estimate of that distribution. And then what we're going to use, so it's a model of trajectories, and then we're going to use this to plan. Now, the transformer is pretty flexible. So you could, for example, ask it to give you a probability for a trajectory. You could use it to sample a physically plausible trajectory. You could also use it to give you a conditional probability over a sequence of states, actions, and rewards given a current state. And that's the capability that we want if we want to plan from a state that we're in now. Now, if we just use it to sample, if you sample trajectories from this density estimator, you will actually get very good samples. So it's very good at representing physically plausible behaviors. This is a bipedal 3D robot, and it will generate trajectories that are hundreds of steps long for this 25-dimensional system that look very realistic. But we don't just want to sample random trajectories. We want to actually find one that accomplishes the task we want. So that's step two. We're going to maximize over the states and actions, as well as the rewards, the log probability of that sequence given the current state. So that's the question transformer is very good at answering. And we can even just use standard sequence modeling tools like beam search to do this, although of course better planning methods would likely lead to better performance. And then we're going to add to this the sum of rewards. So we don't just want a likely trajectory, we want a trajectory that achieves high reward. Trajectory that has high probability and high reward. And we just add this to the beam search log likelihood when we do planning. And we can also add a terminal value function from any value-based method if we want to not plan over the full horizon. That can be really good for very long horizon tasks. So that's basically the method. We can apply it to kind of standard simple offline RL benchmarks. I won't go to this into too much detail because these benchmarks are more or less saturated, but it basically performs on par with the state-of-the-art RL methods. What I want to focus on more is longer horizon tasks. So there's a suite of benchmark tasks called ant-maze tasks that are often used in offline reinforcement learning. And these really test this capability to stitch together parts of trajectories. So the idea is that the robot is supposed to navigate from the lower left corner to the upper right corner, but no single trajectory in the data shows that full path. They show little snippets between random pairs of points in the maze. And you're supposed to put together the good parts to perform this navigation. And in this case, the average score that classic model-free methods get is about 63%. Decision transformer is another transformer-based method that performs behavior cloning without planning, and that performs very poorly. And the trajectory transformer actually gets some of the best results, the current state-of-the-art results, I believe, on this task, and actually saturates, reaching 100% on some of the environments. So this combination of density estimation and planning can work extremely well on some fairly challenging benchmark tasks. And the next thing I want to tell you about is actually another instantiation of a very similar idea. This actually predates the trajectory transformer. It's from 2020, but using a different kind of density model. And this approach will be applied to a vision-based, or in this case, a LiDAR-based navigation task for autonomous driving. So instead of a transformer, we're going to use a normalizing flow model. Planning will be done with continuous optimization using gradient descent, and the goal will be to perform driving. So at a high level, very similar to before, we take a bunch of data, in this case from human drivers, and use it to fit a normalizing flow model, which basically gives you a distribution over paths, basically locations that the car might drive to, given a LiDAR observation. Very similar principle. So it basically answers the question, what are all possible future paths that a human driver might take? You could imagine that if you're at an intersection, it'll assign a high probability to going left, a high probability to going right, but a very low probability to swerving and hitting a stop sign because humans are extremely unlikely to do that. And then step two is we're going to plan. And we're going to plan by doing continuous optimization over a sequence of waypoints to minimize their cost and to maximize their log probability under this model. And the cost will basically encode, are you navigating to the location that the person wants? Like if the person wants to turn left, did you actually turn left while maintaining high probability? So very similar idea, just instantiated in a different way. I'll skip over this part and I'll just show a video of this method in action. So if we actually use the deep imitative model to drive the car, here's what we get. Now, I'll explain what you're seeing here. The diamonds, the orange diamonds on the left, are the waypoints that are commanded. So these are, you can basically think of it as coming from Google Maps. But then the car decides on its own to do things like stop at lights and stop behind other cars and drive on the right side of the road and so on, because that is the only way that it can remain consistent with the data. So what it's inheriting from the data provided by the human drivers is all the social conventions of how to drive the car. And then what it's getting from the planning algorithm is within the distribution that satisfies the social conventions, how do you pick a path that is consistent with the waypoints? And one of the nice things about this is that you can actually compensate for a lot of imperfections in the waypoints. So here, the high-level waypoints are much sparser. They're about 50 meters ahead of the car. So those are indicated by the green crosses now. Here, this is simulating like your GPS system is broken and the waypoints are actually all over the place. Some of them are on the sidewalk, some of them are inside buildings. And the model correctly figures out that it should reject the ones that are inconsistent with this prior data and stay on the right side of the road without driving on the sidewalk. We can, however, give it very strong negative, very strong costs for driving over certain locations that we call potholes here. So those are indicated by the red points on the left. And we can get it to correctly swerve around those potholes if the cost is large enough. Here, our GPS system is accidentally set to UK mode, and it keeps commanding the car to drive on the left side of the road. But nonetheless, the model correctly figures out that it should drive on the right side while staying as close to the waypoints as feasible. Okay, so that was a discussion of how we can combine learning and planning. But in the last part of the talk, I want to briefly go over how in some cases, we can actually get away from planning entirely and yet still get many of the effects that we would associate with planning. And that's going to come back to this pigeon example. One way to think about the pigeon is that just by associating the skills that was trained to do before, that was trained to do with reinforcement learning, it can actually do things that have the appearance of planning without actually planning explicitly for each new situation. Let's talk a little bit about how this might emerge. Let's say that you would like a robot that can cut onions, and you trained a really good skill for cutting onions. And now you put the robot in a kitchen, and in principle, it can cut the onions in this kitchen. The problem is that there are no onions on the table, and it's not holding a knife. Well, a person with common sense would probably figure out that in that situation, you should go and find the knife in a drawer and maybe go and take out the onions and then go and cut the onions. So very simple common sense reasoning will tell you what to do in this situation. But if the robot's skill is just for cutting the onion, it won't necessarily know off the bat how to do this. So here's how we can figure it out. If it has a skill for cutting onions, and the skill has one of those value functions that I mentioned before, then the state where it's holding a knife with an onion in front of it is a high value state. And if it has prior experience, and if in that prior experience it has observed other states, maybe states where it is opening drawers and holding knives, perhaps it can figure out that in those prior experiences, even though it never includes cutting the onions, the state where it's holding the knife also has high value because it's very similar to a state that has high value for its new task. And that means that other states that precede that state also have high value because they lead to a high value state. So that should be figured out with basic dynamic programming. Methods like Q-learning should be able to do this. Of course, in reality, it might have a bunch of other experience for things like making soup and cutting carrots, and it has to learn to ignore that as well. So that's basically the idea, that we can chain together experience from prior data by using dynamic programming, by using basically value-based RL, and essentially perform planning at training time. So propagation of values through Bellman backups can connect prior knowledge to new tasks, and this requires us to run reinforcement learning with prior data, but doesn't necessarily require us to be able to explicitly plan at test time. So here's the setup. Let's say that we have a robot and it has a task to do. It's not going to be cutting onions. It'll be grasping a ball from an open drawer. If at test time the situation changes and the drawer is now closed, of course, the robot won't know how to do if all it has is this drawer opening skill. But if it has a bunch of prior data of other skills that do not involve picking up the ball, but involve things like opening drawers, closing drawers, opening other drawers, and moving other objects, perhaps you can combine these to solve the task. So precisely what the setup is that The task has 0, 1 rewards. You get 1 if you pick up the ball and 0 otherwise. You have to learn the task entirely from images, and you only see data of the current task from a single starting condition. Your prior data has no reward at all. So the reward label for all the prior data is 0. It doesn't accomplish the new task, but it does show you how to reach the starting state for your task from some other conditions. It also shows you a bunch of stuff that is useless. So it's not actually sorted or curated in any way. And the algorithm that we're going to use is just a model-free, offline value-based RL method. I won't talk about the algorithmic details too much. I don't have the time for it in this talk, but if you want to find out more about the algorithm, you can look up conservative Q-learning and you can find out how it works. But roughly speaking, it's basically a Q-learning algorithm. And if we run this on this combined data set, we actually get behaviors that, that quantitatively perform very well, but qualitatively exhibit some things that kind of resemble that pigeon. So if we put the robot in a state where the drawer is open, it will of course pick up the ball. If we put it in a state where the drawer is closed, it'll open the drawer and pick up the ball, even though it's never seen those two things together. But it's seen drawer opening and it's seen ball picking, and it knows that it has a high value for picking the ball if the drawer is open, so it'll open the drawer. And at test time, it's not doing any planning. At test time, it's just running the policy. If the top drawer is open, it'll close the top drawer, then open the bottom one, and then pick up the ball. So it can stitch together 3 steps. If there is an obstruction in the way, it'll lift the obstruction, put it away, open the bottom drawer, and then pick up the ball. And the same thing can work in the real world. So similar setup, although with fewer tasks here, and we'll figure out that it can open the drawer and pick up, in this case, the stuffed animal, even though it's never seen these 2 stages together in a single trajectory. All right. So I should wrap up. I'm a little bit over time. So just to summarize, I talked about how you can plan over learned skills, how you can plan inside the data distribution, which provides you with a more fine-grained planning paradigm, and how you can actually get some of the benefits of planning without planning at all using dynamic programming. So the main takeaways that I'd like you to have from this talk is that data-driven or experiential learning can provide representations for planning. And these representations can take many forms. They can take the form of closed-loop skills, skills that expose capabilities like value functions to a planner. It can provide action representations and dynamics. So learned models can provide action representations and dynamics over which to plan while remaining close to the data distribution. Or it can simply serve to provide dynamic programming and stitching where value-based RL methods can directly solve a kind of a planning problem. But all of these things revolve around the same key theme, which is that data tells the system how to handle complex input-output relationships to attain near-term outcomes, and planning, whether explicit or implicit via dynamic programming, uses these relationships to solve long horizon tasks. All right, I'd like to thank the students that carried out this research, and I'd like to thank all of you for listening. And if we have a little bit of time, I'd be happy to take some questions.
Yes, thank you, Sergey. Very nice talk. Thank you very much. So I think we have some time for questions.